All right, maybe we can get started. Today we're mostly going to spend some time talking about efficient training. We'll finish up last time. We'll do a tiny bit on what that looks like, and then we'll talk a little bit about efficient inference, which we'll keep going with on Tuesday. All right, so we're in the middle of everything, so a lot of logistical stuff happening. Homework 2 in progress. Hopefully folks have gotten a chance to take a look. Sign up is happening right now for presentations. I actually have not seen that many folks sign up yet, so if you want to be quick and grab a slot, that's great. You should do it sooner. And finally, I'll try to release project information probably this weekend. Very, very similar to the presentations. Form teams. You'll propose a project idea, and I'll chat with you folks about what we can do for it. So for where we are of the class, we're actually making good progress. We're heading towards the end. Efficient training and inference, as I mentioned. We'll spend a bunch of time next week talking about evaluation, which is a pretty big topic. So we'll see benchmarks. We'll see all sort of techniques that people use for figuring out if their models work. We'll talk about agents, which is maybe the newest thing for this class. And there'll be new pieces, including papers that just came out. And then we'll kind of circle around and get back to reasoning, because there as well, people are doing a lot of active research. Plan for today, let's finish up the last few slides from last time. If you recall, we were talking about RLVR, which is reinforcement learning with verifiable rewards. We're talking about GRPO, this loss function that's very popular for training with RLVR. And the last things we'll talk about are a couple of reasoning tasks that this kind of thing is really good for. Then we'll jump into efficient training. We'll talk about why we need it, mostly in the sense of what scale these models are at. We'll talk about something called flash attention. This is a really simple technique that speeds up training. It's based on a very nice trick, which is make sure you use your GPU as effectively as you can. It's not an approximation, which is interesting. You're not trying to sort of cut down on compute by using a cheaper approximation. It's exact, but it's much faster. And then finally, we're not going to have too much of a chance to talk about it, but things like parallelism will be pretty important. If you take kind of an ML systems class, you'll spend a whole bunch of time looking at different forms of parallelism to kind of speed up that training process. Then we'll start with efficient inference. We'll really probably have kind of a chance only to talk about the first piece here, which is speculative decoding. A very fun technique that can really speed up how fast your models produce tokens, also based on architecture. So you've probably seen things like speculative execution, same basic idea. All right, so let's go ahead and finish up last time. The motivation for what we talked about last time was, yeah, we figured out how to use RL for this process of alignment, which is to say we took human feedback, we built a reward model using it, and then we went ahead and built this RL loop to train our models in such a way that they give desirable, preferred kind of responses. So then we said, OK, well, maybe RL can be used outside of this alignment process. Maybe there's other things we can do with it to improve our models, but in a different sense. And then what we said, OK, let's build a good model. Let's forget about human preference data. Let's see what other things can get plugged in and serve as a reward model. And maybe we don't even need a trained reward model. Maybe a reward function is good enough. Really, all we need is some way of saying, is this output good, or is this output bad? And if we have that, we can basically do this RL loop with it. All right, everybody agree with that? Cool, so the most natural place, of course, is, well, the reward is I have the right answer, or, of course, I don't have the right answer, and that makes things really simple. And notice that this applies to the kind of problems where it's not just spit out an answer. It's solve the problem and reach some final point. So things like math and code were our two examples here. Of course, there's other things that you can do as well, and I'll show some examples. All right, everybody comfortable with this part from last time? Any questions that we didn't get a chance to? Awesome. OK, so basically, initially, when we did RLHF, we had one particular kind of training approach for the RL loop, and that was this thing called PPO. And we kind of showed some details of it, although we didn't talk about it too much. But we basically said, look, PPO is a very general technique for RL training. It's not something that's specific to RLHF. It just happened to be the case that people started using it for RLHF. But I don't need to specifically have a preference model as my reward model. I can apply it to anything else as well. So folks started using PPO, basically, with this notion of a verifier as the reward function or reward model. And what we saw is it's pretty simple to use. It has some fancy looking notation, but there's not that much going on when you look at the objective function. All right, so what do we have here basically? This is written in more standard RL notation. So you kind of have to translate what all of these terms mean in terms of our actual model, but nothing super hard to interpret. The AT you're seeing over there is the action that we're taking at time t. ST is the current state that we're in. And then that's pretty much it. The capital A over there is the advantage. This is how much do we gain by taking this particular action compared to the previous policy. And then the term on the right that you're seeing over there, this beta KL term, that's just this regularizer that we've talked about in the past. It says, hey, don't change my model too much, which is something that matters quite a lot for language models. We don't want them to forget their general capabilities. OK, so this advantage, again, defined in standard RL terminology, is the Q function, which says, hey, what cumulative expected reward do I get when I'm in the state ST and I take this particular action AT, versus the one I would get from following the standard policy I'm using, which is my value function V of ST. OK, if you haven't taken an RL class, not really critical. The point, though, is that this thing is not something that we know. We have to estimate it. The A hat over there is whatever estimate we come up with for PP. OK, the only other piece that's slightly different here is that we have to do importance weighting. That's the first term in front of the advantage. We generated our response from our old policy, but the probability is different. It's based on our current one, which is pi theta. So let's go ahead and reweight. OK, there's one more trick that we sometimes see, which is this clipping idea. Supposing that the advantage is something that's just too big or too negative, let's go ahead and bound it within some range. And that's this 1 minus epsilon, 1 plus epsilon. And then we can go ahead and combine these two guys as well. So if you want to look at what's actually happening in an RLHF training loop, this is really the function, really a combination of these two, that's being optimized. OK, cool. So we don't really care about this too much. But let's see what we can do to modify this guy to make more sense for these reasoning tasks that can be verified with a verifier. And really, we're going to do exactly two things. One thing we're going to do, basically, is rather than running this once, we're now going to say, hey, let's get a bunch of responses, not just one. And let's try to pick out which one's the good one. And let's try to push the model toward that good one. The second thing that we'll do is the thing we've talked about. When we go compute this advantage, it's not going to be based on these estimates of Q and V. We're just going to plug in our actual reward coming from our verifier. So those are the only two sort of things that we're going to do that are going to be special. Beyond that, there's nothing really too different in this RLVR GRPO function. Too many acronyms, but is everybody OK with this? Go for it.
Isn't our Q function and V function going to have a very, very sparse action space? Like, the action space is any next token.
In this case, yes.
So theoretically, the action space spans V to the n, where n is the number of characters in your response.
Keep in mind, we're not going to do tabular RL, where we keep a gigantic table. These also are models, right? So all of this is going to be based on functions, not on some giant lookup table that you use.
But even then, like, you can have n tokens out. You know, if you want to model the probability distribution, even among the potential outputs that can come out that are reasonable, that's huge.
No, it's just another language model. This pi as a whole is just that probability distribution, right? That's exactly what we're using. Now, you're right, and this is really the motivation for getting rid of this stuff, right? I don't want multiple language models that serve in all these roles. I want to throw some of these out, and let's say I have a verifier. It gives me a reward. I don't have to do anything but that. So you're actually completely right, but just keep in mind, these giant distributions are exactly the thing that we're doing in the first place. Cool. OK, so let's check out GRPO. So this is group relative policy optimization. Like I said, we are really awash in different acronyms and names, but they're mostly pretty simple. So this is something that the DeepSeek team introduced. Initially, this is what they did for improving performance on math problems. These are exactly the kind of verifiable data that we want to have here. They also used it in general for R1. Let's take a look at this loss function. It's almost exactly what we saw before, the combination of the two versions of PPO that I showed. Right? So you're seeing the version that doesn't have clipping and the version that does have clipping. We'll run them through a min. We'll be more conservative. Take the more reasonable one. The only big difference that you're seeing here is this 1 over g thing. And let's try to go ahead and figure out what's going on there. Maybe I can zoom in to make this slightly easier to see. Or maybe not. Does it really not let me? Here we go. All right, so what are we doing? We are going to train a model whose weights are theta. This is our language model, as always. What's happening here, in my expectation, is I'm sampling Q from some distribution over queries. These are our prompts. Think of these as prompts that have reasoning responses that produce some final answer that we can verify. So these can all be math problems from some math data set, for example, or anything else, but they do have to be verifiable. So I'm going to sample one of these guys. And then what I'm going to do next is I'm going to take my model as it is, and I'm going to go ahead and sample G total responses. So each of these OI over here is just running my language model, right, for a given prompt Q, produce a response with the current language model as it is. This is theta old. So this is before I've taken steps, right? Of course, we'll take some steps, and then we'll get a fresh batch of responses and keep this process going. But everybody OK with this so far? All right, so I've sampled the problem, and I've sampled G, capital G total responses to this problem. Next, I'm going to run this exact procedure that we talked about. The loss will be the average over these advantages. Again, they're summed up over all of these guys. We're using this importance weighing and clipping. And then finally, we're still doing the same thing that we always did, which is regularizing so that I don't change my model too much as relative to the base model originally. So notice that what we have here are basically 3 different models going on. One is pi-ref, the base model before we started fine-tuning at all. We have phi old, which is the model at a current step of training before I take the next set of steps. And then we have pi theta over here, right, which is going to be the one that I'm currently training before I sample my next batch of data. That sound good to everybody? Cool. So this is pretty much all that's happening here. Now, to actually instantiate this guy, the only term that we really need to look at is we need to define what the advantage looks like. What is this AI? And there's going to be an advantage for each of my responses. So here, the way we'll define it is by basically taking our rewards, which will come from our verifiers, and saying, OK, how good are they relative to other things in my group? So that's going to be very, very simple. It's literally just normalizing it. It's going to be this exact function, compute the mean of all of my rewards for each of the G generations I got, subtract that mean, divide by the standard deviation. So I'm just saying all of my advantages for each of my responses are just the normalized rewards that I get. And we'll define those rewards in a second. But that was the only thing that we haven't yet defined in GRPO. If you look at all the other terms, they're exactly what we've dealt with before. So we could go implement this without too much trouble. All right, any questions so far about this part? We're taking G responses from our model, and we're basically trying to figure out kind of which of those responses should we push our model towards, and which of them should we push our model against. So some of those responses have a big advantage because it's much larger than the average. Then we'll push our model in that direction. We'll tune our weights a lot in that direction. On the other hand, if there's some big disadvantage or not much advantage, then we won't do that with the model. Everybody agree? Cool. All right, so let's go ahead and fill out what these RI actually mean. We're going to do the simplest possible thing. Let's take our verifier and say, did you get it right or did you get it wrong? And that's called an accuracy reward. It's literally just tracking correctness. So this is the big advantage of having a verifier. It can actually spit out 1 or 0 for having gotten this problem right or wrong. We'll do one additional extra thing, which is interesting because it's not really about getting the answer right. It's more about convincing the model to do a certain kind of behavior that will be useful for us. And that's the second component you're seeing here in the bottom, format rewards. Basically, we're telling the model, you should have these think tags. And you should do a bunch of steps of thinking in between them. So this is kind of similar to how when we were doing things like chain of thought, we were trying to encourage the model to output many steps, right? Now, we did that encouragement in a prompt because that was, an inference-only technique. In this case, we're doing something during RL itself. We're encouraging the model through the reward to say, yeah, make sure you have a bunch of thinking elements in there. Now, these thinking tokens, right, they're not going to be tokens that contain the final response. They're going to be tokens that are meant for the model to work through a bunch of different steps. But the principle is the same as what we saw before. So again, this is something very simple and cheap, right? I don't have to train a separate reward model like I did for preference data and keep that model around and constantly sample from it. Instead, I run my correctness function, which is just literally a check. It says, is this the right answer or not? And then I look for whether there's these think tags, which is basically free as well. So here, the advantage is computed almost instantly at no cost. But of course, the downside is I do need to have that verifier. So I can only use questions where I know what the correct answer is. All right, everybody comfortable with what we've seen here? So the story compared to RLHF is, in RLHF, I was doing something fairly general, which is this human alignment. But I did need human preference data, and I had to train that reward model, at least if I was going to use RL. We had techniques like DPO that tried to do direct training, but there were some downsides to supervised training as well. We saw that. In this case, we're doing something different. We're saying, hey, we want a model that is good at reasoning for a particular class of problems. We have the solutions for those problems with the answers. We're going to create a very simple reward based on those answers and train on these guys. And that's pretty much all that RLVR really is. All the rest is going to come down to, hey, how can we make this process cheaper? Notice that here we do have to do a bunch of these generations from the model again and again. Awesome. Questions? One question for you guys is, well, could you actually write code to build one of these training loops and train a model? We might try it for the homework. Unfortunately, our reasoning is going to have to be very restricted. Naturally, we need a model that has some chance of producing responses that pass the verifier. If our entire group always gets it wrong, it will never see any reward, right? The advantage will always be 0, and there'll be nothing to do. So if you do want to play around with this stuff, either you need a model powerful enough to get problems right sometime, or you need to restrict yourself to some very simple reasoning problems. Ideally, ones that are not even in natural language, because that will require a model of some size. So we might try this for the homework if we can figure out a good setting where people can try it. It's not going to be super easy. All right, other question. What if you always get it right? What happens in that case? What will my loss look like? Yeah, I mean, we can see what's going on here, right? If R1 through RG are all correct and equal, then what will each of these AIs be? 0, right? And if you plug in 0 over there, nothing happens, right? There's no signal. You will never take any steps. So really, you do want some variance here. You want these numbers to look different. And you certainly don't want them to all be 0, to all be wrong, or all be right either. Because then you have not much you can really do. Cool. All right, so that's pretty much it. I wanted to show a couple of examples of where this works. We'll talk more about this stuff when we do evaluation and benchmarks. But this is sort of the most popular math benchmark for a while. And really, like 01 when it came out, it was especially exciting because of how well it does on this math contest. It's called AIME, or AIME. It's kind of a high school math competition. It's not either very easy or very hard, but it's challenging enough for these kinds of models to have some trouble but not get everything wrong, which is exactly what we talked about. OK, so what we're showing here basically is that there's 15 problems from 1 to 15. That's this x-axis. The first problem is easiest. The 15th is usually the hardest. And you're seeing on the y-axis a whole bunch of models and kind of what they performed in each of these guys. And by how they performed, I mean that we tried multiple times for each model, for each problem. We averaged that performance. The more shaded green it is, the more you got it right. The closer to red, the more often you got it wrong. So you can kind of see that for the very best very best closed source models on top, you actually do pretty well. You get everything except the hardest 2 or 3 problems right. So this was Gemini and O3, for example. This plot is about 6 months old, by the way. Now, if we go down to open source models, they're still pretty good, but they will get problems more often wrong. And finally, notice that if you use the really fast versions of models that are not good at thinking or reasoning, you'll also get stuff wrong a lot too. So this is a pretty good benchmark. Unfortunately, of course, as soon as it gets released, it makes its way into the training data. So it becomes not super useful because of this contamination issue. The time where this kind of exam is the most useful for figuring out which models are good is like the week after it comes out, the next one. And even then, the problems are sometimes too similar to other problems that the models have seen, so you don't get a very good gauge then either. Any questions about this? Cool. Now in the, last 6 to 9 months, we've really gotten so good at these AMY problems that they're not that interesting. People now work with harder Olympiad problems, but there's a catch. The Olympiad problems are proof-based. So it's not as simple as saying, oh, you got this numerical answer correct or incorrect. You have to build a system that can check whether the answers were right, which is to say to read a bunch of proofs. But even so, this summer, both OpenAI and Google competed with their models in the International Math Olympiad, which is kind of the most prestigious of these math competitions. And they both got good results, good enough to get a gold medal, which is something like 60 to 100 competitors get a gold medal. That's usually like the top 10, 15%. So we've gotten pretty good at those kind of proof-based problems as well. Basically anything that has some reasonable technique to get to an answer, these top models at least can pretty much do it. Even research level stuff, although there it's a bit more complex. They can do the kind of calculations that a strong student would do in a day or two, but they can't do like full theories that take time and creativity to do. Okay, so this is all for math, which is still the kind of #1 domain in addition to code for these reasoning models. I am going to take advantage of the class and plug some stuff I've been working on. This is for theoretical physics. Very similar story. We've built this benchmark that has a number of these problems. You can see kind of where performance is at. It's very similar. There's 5 of these categories of problems going from easy undergrad to research level. And you can see how performance falls as you get to the hardest kinds of problems, which even the best models can't solve too often. But even open source models can do a decent job at these kinds of undergrad problems that you're seeing on the left. So even for domains that are not strictly math, you can now actually do pretty well. The question is, how far can we go with these things in general? And that's an open question because these models have not seen a lot of data on every possible domain. There's lots of areas where they have no idea. And the question becomes, how do we get the right kind of training data to familiarize themselves with this stuff? All right, and that's it for the part that we left off of. Let's take a quick break, and I can answer questions from anyone. Go for it.
I think I'm still confused on the reinforcement learning stuff. Is the output is the next token, right?
It could be a whole sequence here.
Oh, okay.
Yeah, there's nothing stopping us, right? The only question basically is, where do we get signal from, right? And here we can do that. There's nothing problematic about it, right? You can compute the probability of an entire sequence, right? Same way that you would do it by chain rule normally.
So that's what like the action is called?
Yes.
The next
Yeah.
sequence.
Yeah. Exactly.
Those probabilities get really small, right?
Well, we're not going to directly compute them as they are. You take a log, right?
Sure, that makes sense. Well, I mean, in this case, it's not approximate. It's just right.
Yeah, you'll get underflow, but we can deal with it. That's a standard thing that will happen to us in all language models, basically.
How do we deal with the underflow? We just use longer integer, longer floats?
No, we take a log. We don't deal with probabilities as they are. We deal with log probs.
Okay, I thought the underflow also applied to the log probabilities where...
I don't know, log is pretty powerful, right? You'd have to have unbelievably tiny numbers. You can compute them to have that issue.
For some reason, I was thinking of like if you hit the boundary and you flipped constant lines.
I mean, there are bugs like that you will not normally see, but it's possible.
That makes sense.
But they've gotten smaller, right? They're trying to make big ones.
Sorry, yellow me, one nothing. Go for it. Oh, so Q and V are both different functions that show up in the reinforcement. So both of them are measuring almost exactly the same thing, which is your expected cumulative reward. And what the Q function is saying is, if I'm in this state and I take this action, what do I expect to see in terms of average reward? So not just for this state of state, but for all future states. Assuming that I follow some policy after the state in action here. The V function is the same thing, except that it doesn't let you explicitly make a new action like T. It just says, hey, if I follow my current policy, starting with the same thing, what is my expected cumulative? So these are the functions that we use to kind of see, like, hey, in the long term, what do I expect to get? And what's the difference between those two things is saying, well, suppose I change my action, now my current policy station is something else. What do I get? Suppose, for example, you have some stock trading strategy. Based on a strategy, starting with your current money, whatever it is, right? You expect to get $2 million over the course of your life, right? That's your V function. Now, suppose you say, hey, well, starting from the same pile of money, I decide to trade my NVIDIA stocks right tomorrow, right? What do I expect to see? Right? And assuming that you sell those stocks tomorrow, but everything else you do is still your normal strategy, what's the difference? Things in the long term. That's what we do there.
So these are fixed functions and then you can.
Well, they are fixed functions, yes, but unfortunately, we don't know them, right? So we also have to test these functions. And because these functions have very, very big domains, right? There's lots of states, lots of actions. For that reason, we have to test. We're going to have some functional approximation for them. And we're not going to talk about how to do that, but there's a bunch of different techniques for that. And that 8 half, what you're seeing, is the actual approximation for us. So this is our This 8 half over there is some number, right? And we're able to actually get that number. But it's not the real version of the approximation. It's an estimate. Yes, so here we're dropping any pretense of Q and VR. We're no longer talking about, oh, you know, over the long term, here's what I expect to see. We're saying here's the reward or not. It is literally just saying yes, can you and go push in the direction, that's all. So nothing else is happening. Well, there's 2 things, right? One is we're using these cheap sources of signals instead of trying to estimate our future information, right? Second, we're doing it along with groups of responses. So rather than just sort of, well, I got, you know, an answer once, and then I'll move to a new problem, and I'll get another answer. I'm getting a bunch of answers for a problem and pushing in the direction of a good one. So it's kind of like visiting the same state multiple times and making sure you cover it.
So instead of finding.
It wouldn't really be binary in that case either. It's just some general advantage. But you're doing it for one token or one sequence. Here we're doing it for a group of different Yeah, some combination of 2. This has to be a number, right? The final thing is always a scale that you're using. Yeah. But you can combine all the different rewards and exactly. And you can incorporate extra terms. There's another kind of right? Yeah, but the problem is it didn't allow to get a scalar because you have a partial derivative. You can't just have a vector.
Yeah.
No, V is the one for positive. It's not V star. Right?
Yeah, I'm just trying to.
We don't even know V stars. V star, we just extract out the positive from it.
And my like notebooks and like the charger.
Sure. So V respect any positive I. In our case, the policy is just the old language model, right? So he says, okay, well, for the old language model, here is the action I choose, which is to say, here's the token. And now we're saying, well, if we do, what would we get first? What is the difference? Or is it worse?
Sure, yeah.
He says, hey, I'm the action is not the action I sampled from the policy. In this case, it's the one that's from.
The left of it. I mean, it's fine.
The point is, like, what's the value of getting something different compared to what I had before? And it's going to be impossible. Either push the model more in the positive direction or against the negative direction.
Yeah.
You see things like, I mentioned this link thing, which I love more models really like. People kind of penalize it and say, hey, don't do that. That's the check. The only problem is, like, if I'm doing things like reasoning, where there's a hard current notion, if I just try to guess the policies, I may teach the model to do stupid things, basically. That's true.
Resume investments.
I don't know if we need it.
You can probably do the entire project in $2.
That's fair. Yeah. No, that's a good stuff.
So the I'm thinking steps, right? And each step is in the direction.
Here's my idea.
That's the only thing.
Because these days, the only one
Before they even get to it.
do it, I think you're just debates.
Well, unfortunately, I still have to fix things, right? Because over here, right? The probability is
When Claude, it's like you just make some like.
yeah, the whole reason here is
That's easy.
So you'll.
that's the only real thing.
Easy person. We can.
So the biggest issue you just run vanilla R as soon as you so you run
It's great. Why? Service records. Just one. So that's the most important thing.
Yes.
Because the big files,
The reason for that is for verifying that the responses.
big files,
You cannot say, oh, this token's good. The correct.
it does not work. Or sorry, it does not work for the pages. It made it so that if I wanted to start making I would
I just say, hey,
they're not going to be like an hour and a half.
for the syntax,
I do development, and then I have every branch. Every branch of music is like minutes to.
we'll see. That's what we're doing here, is we're saying, Which one should be more?
Good ideas.
My thing is, I can give you the probability of a whole sequence. How is it?
The session took fire.
So it is like high theta, first token, very high theta, second token.
Most of the time, I did work on a very contested project.
One big probability is make the probability of the sequence that corresponds to the probability of the sequence. So that's what's going on here. Yeah, actually, to the point, you can trace out the expressions.
Yes.
It'll make it much bigger. This is exactly what the grade is. But your questions are very good.
Yes, you should be managing the entire repository. You should be managing all of the
Cool. Thank you for all the questions, folks. Let's start chatting about training. We're not going to get too deep into this, although, again, if you take a systems ML class, you will spend your whole time doing this. Let's figure out the motivation for training, which we've kind of hinted at a bunch of times, but haven't gotten too deep into. I will show an example from a couple of years ago for Llama. Llama is Meta's family of open source models. Here's a quote from their paper. We estimate that to develop all of their models, including the biggest ones they released, they used 2,000 GPUs. This is the A100, which is a popular card a few years ago. And it took about 5 months in total to develop all of these. Now, this is not one training run. This is all of the runs they did for all of the models, all the experimentation, etc. But this is pretty typical. It is usually a number of months, and it's usually a number of thousands of these kinds of GPUs. And each of those guys is a data center GPU. These are not things you can just buy on the market and run in your desktop. You typically need to buy a data center, more or less, or at least get some space in one. Typical costs are around $50,000 for one of those guys. So you can get a sense of what it costs to build together a cluster with multiple thousands of GPUs. Pretty expensive. And of course, these things break all the time. So really, you need much more than just the 2,000 you'll use for training. Here's another model, OPT, very similar. For their 200 billion-ish model, it took them about 1,000 of these GPUs. And here's a plot from the Llama paper, which is pretty fun to read. You can get a sense of how much these different models were actually using in terms of cards and hours. So for a small 7 billion parameter model, that's usually the sweet spot for us to kind of play with at home. To train it, you still needed 80,000 GPU hours. Okay, now a different way of kind of thinking about this stuff is, I don't know, it costs about $30 an hour to get a node with 8 A100s, B100s, whatever. So you can get a sense of that. If we divide that 80,000 by 8, we get 10,000. Right? 10,000 times $30 is like $300,000. So even for these small models, it's not exactly cheap, although we're getting closer to a reasonable number. By reasonable, I mean, I don't know, a good academic lab might be able to get that funding. But if we're talking about, these 70 billion or 100 plus billion, you're in the 1 million GPU hours, at least 10 times as much. Now we're talking about multiple millions of dollars just for training one of these models, so it's getting a little bit out of reach. You can also see how much power consumption and carbon emissions you get from these things. That's itself kind of a problem, though I should say that it's not really training so much that is the biggest factor here. It is when you run these things at inference time consistently, you end up paying more. Because each of these models is served for a longer time period than just the 5 months it took to develop all of them in training. Okay, everybody okay with this? Now this is also the fun part. If you go work for a company, you can ask about how big their cluster is and what you can get access to. There are places where even individual researchers can get 100 GPUs at a time to run kind of fun experiments. Okay, so let me talk a bit about sort of what we have to think about when we talk about using these GPUs. They're not black boxes where you just run stuff and let it happen and you don't think too much about it. If you know what's going on in the way that GPUs operate, it turns out there's kind of like very big savings that you can get. All right, so let me give an example of this that led to this technique called flash attention. GPUs have memory, but they have different kinds of memory and different amounts. There is a very small amount of very fast memory, and then there is this much larger amount, which is the thing that we talk about, the 80 gigs, of what is slower memory, although still relatively fast compared to CPU memory. Okay, so what's the story about that then? If I do have this very fast memory, I should use it whenever I can. Why can't I always use it? Because there's not that much of it, right? And we're talking about a lot of different model parts that are very big. So I can't always use it, but if I have any opportunity to, I should. Okay, so we're going to see how this is done in this technique called flash attention. It's a very simple plug-in replacement for standard PyTorch attention, but it uses some ideas about the GPU, which is exactly what we talked about, and we're going to walk through these right now. Now, what's the point? This can make training 2 to 3 times faster, which doesn't sound like a gigantic improvement, but again, if you go to your 5-month development process, if you make that 1 month or 2 months instead, that's actually quite a big gain. So any kind of 2 to 3 times improvement turns out to be pretty valuable. All right, so here's the picture from the paper. The thing that we'll talk about is on the left here. This is kind of the memory hierarchy. A small amount of very fast memory on top, and then as you get lower, there's more memory, but it turns out to be slower. So you want to stick to the top of that triangle as much as you possibly can. And of course, when you can't, you have to go down further. And we'll see this a little bit. This picture is way too complicated to read, but the operation that we're going to do stuff on is just going to be attention. So that's almost entirely what we'll talk about here. Running the basic attention operation that we've talked about. You can actually see it in the corner over here. Softmax of Q times K, all of that times V. Our goal is going to be, how do we run this procedure as much as possible within the fast memory, and how do we avoid having to go back and forth to the slower memory, which sort of the vanilla implementation, unfortunately, will do. And by vanilla implementation, I just mean what you get when you run PyTorch, the one that's written in PyTorch. And this plot on the right is showing you basically the latency for these things. For PyTorch, all the operations that you'll end up doing when you do this is going to add up to some number of milliseconds. And then if you instead replace it with this flash attention variant, it's much faster. But however, you have to do GPU programming to develop this kind of thing. So you get some gains, but you have to drop down to a lower level, do some programming that's closer to the hardware, and use that guy as much as possible. So that comes with its own challenges, but that's kind of what we'll take advantage of now. Okay, so let's jump into this flash attention idea. Basically, again, the motivation is we have these different kinds of GPU memory. The thing on the very top, static RAM, is extremely fast. You can see the throughput over there. It's almost 20 terabytes per second. That's extraordinarily fast, right? And you get a little bit of it, which is 20 megs. That's it. So super fast, but the quantity of this memory is extremely small. It's very expensive. Then when we go down, the high bandwidth memory, that GPU HBM, as you can see, is much slower. We're down to 1.5 terabytes per second, but this is where we get a lot of it, right? When we talk about video memory, 40, 80 gigs per card, this is that memory. Now, of course, we can go away from that altogether and move to main memory at the CPU level, not even on a graphics card. And then we have dynamic RAM, and it's much, much, much slower. So now it's 1,000 times slower, but we can get a lot of it, right? Typically, what you'll get in a data center is just vast amounts of memory. And of course, we can go even slower than this, although it's not useful for model training anymore. We can have things like hard disks, right? Which are even bigger and even slower. All right, everybody okay with this idea? So the plan for us is going to be, let's use that top triangle in orange as much as we possibly can. And let's try to avoid going back and forth to the green one, again, as much as we possibly can. But as you can see, there's no hope that the entire model can be hosted in the fast memory, because it's only 20 megs. So if we have large models, there's no chance of fitting terribly much in there. In fact, even very basic vectors that we have to create don't fit in this guy, and we'll have to do something different for them. Cool. Everybody okay with this story? We'll see how to do it in a second. Okay, so again, these are the details. So we don't have terribly much, 200 KB or whatever for each of these different processors that you have on an A100. Adds up 20 megs in total. Our total HBM, so 40 to 80 gigs, and we're not going to use the HBM at least as much as we can. Okay, so the tricks that we're going to learn for how we do this process are going to be very simple. One is going to be called tiling. And this is the standard thing that you really do when you have some big computation and you don't have enough space for it, right? You do a part of it, the first tile, you get some results. You do the second part, the next tile, you get some results, and so forth. In other words, break up your calculation into tiles, these smaller parts, run it on each of the tiles separately, and aggregate those results. So very standard idea. We'll just design a version of this specifically for attention and specifically to run on GPUs. The second bit that's going to be very interesting is recomputing. And what we mean here is the following. When you think of doing backward passes, you have a bunch of stuff that you normally store that you computed in the forward pass. In other words, all those intermediate computations that you did that took place in the forward pass, from the input all the way to the output and the loss, you normally store all of those guys because all of them are used in backprop. Convince yourself that's true, write down the calculation. Now that's a problem though for us, right? Because that's a lot of different things, and we do not have enough memory, at least fast memory, to store all of those intermediate components. So what we're going to do here is we're going to say, let's give up on storing some of them, and let's just compute them again during the backward pass. And now you might say, okay, well, why is that good? Computing things twice takes longer than computing them once and storing them. That is normally true, right? That is the normal trade-off that you'll have. However, if the recomputation happens in this much faster memory, that might be okay. Maybe it's better to compute something twice in fast memory than have to go send it to slow memory and read it back from there again, even if I only did the computation once. Everybody get that intuition? Basically, the idea is if I'm so much faster, then doing the same work multiple times is still far faster than doing it once but having to use something slower for it. That's going to be the trick here. We'll see a little bit down in a couple slides exactly how that works. Okay, so let's get back to standard attention. Let me show you an implementation of what it normally would look like. It's just a basic operation, but we're going to take care of where things are actually being stored. So here's the operation itself. This is algorithm 0. This is going to be the version that doesn't do anything smart, right? Okay, so we know the inputs. They are going to be Q, K, and V, right? These are our matrices for the queries, the keys, and the values. We've already computed these guys. They're available at the input. Hopefully everybody remembers what these mean from the first couple of weeks. Okay, so the very first thing we'll have to do is to compute Q times K, right? And we'll have to load into our fast memory blocks of Q and K, and then we'll compute their output, which is S. Think of this just as the matrix of dot products of queries and keys. Okay, after we compute this big matrix, let's call this thing S, we'll have to go write it back to memory, right? HBM, the slower, bigger memory, because it doesn't fit in my fast memory. Okay, the next thing I have to do is to compute softmax, right? So I have to read S, again, the whole matrix, take its parts, compute softmax, write it back. Then I have to multiply the softmax matrix P with my value matrix V. Again, go ahead and compute this guy, call it the output O, write it back in. So we have all this back and forth where we're creating a result, storing it back in memory is a big piece, creating another result, and so forth. So the trick that we're going to use is basically saying, hey, I can do many more of these steps all at once on pieces or tiles without having to do each intermediate step separately and load up its components for the next step. So rather than saying, hey, do step 1, which is Q times K, load it, and then read it back when I'm ready for my next calculation, I'll just kind of go directly, create pieces of all of these things, and skip to the last step just by going through and working on these tiles. And I'll show you what I mean in just a second. So the first thing we'll do is try to look at how we normally compute softmax and see if we can do it on separate parts. Okay, so let's go ahead and take a look here. Here's what I would normally do if I'm just running on a vector softmax. Let's call that vector x. Well, one thing you can do in the most straightforward way is just say first take all of the elements, take x of those elements, add them all together, create that denominator, and divide each component by that denominator. Okay, why is that bad? In fact, we were just talking about this. All right, so for example, if I have a value of 300 in there, what will happen if I do x of 300? Yeah, these are huge numbers, right? And if I do things like x of 300 plus x of 1,000, nothing will work there. Okay, so a more numerically stable way of doing this kind of thing is to first normalize all the values before I do anything with a denominator. This is not that different from taking a log. Let's first compute m of x, which is the maximum entry in all of my vectors components. So that's the maximum over all the xi's. This is this m of x. Okay, now what I can do is instead of exponentiate each component of my vector, I'll exponentiate each component minus the maximum. Okay, now why is this good? Well, because I've now made all these values smaller. These values are all either negative numbers or 0. Everybody agree? Any xj minus max of xi is at most 0 if your xj is equal to xi, otherwise it's negative. Does that sound good? Okay, so these values are now smaller. Everything you see in this f of x over here, which is x of each entry minus the max, these cannot be too big. Great. So now we're good. We can sum up these guys to build up our denominator. That's this L of x, just a summation of all these f of x terms. Okay, now we're almost ready to go ahead and compute the final version. I could just go ahead and divide f of x, which is this vector of exponentiated guys, by L of x, which is my denominator. And notice that this minus m of x will cancel out on top and bottom, right? It's exactly the same thing as multiplying by x of minus m of x. On top and on bottom, cancels out. So this is numerically stable. None of the values are going to be that big, so we're comfortable with this. Okay, everybody okay with this? It's an alternative way to write down the formula for softmax in a way that you can actually compute it without overflows, without any stability issues. Okay, now so far, we actually haven't done anything, right? So here I still have to load up this entire vector and then compute softmax on it, right? We haven't split it up into parts. We haven't done anything clever. Let's see if we can do that. So suppose, for example, that rather than saying, hey, I have this full vector, let's say I can only ever look at one part of it. Suppose my memory cannot fit more than 1/2 of this full vector ever. So I can never load up the full thing. I can load up the first half or the second half, but I still want to compute softmax over the whole thing. Everybody okay with this motivation? So this is what I mean by tiling. We'll split up our vector into 2 tiles, and all of our operations, even though they require all the information, will be done over the 2 halves. Or I can split it up into more tiles, hundreds if I need to. Again, I can never look at the full vector. I can only look at parts of it. But I need a final output that's a function of the full thing. Everybody okay with this motivation so far? Cool. All right, so for the simple version with 2 components, I have x superscript 1, x superscript 2. The first part of the vector, the second part of my x vector. My memory can fit x1 or it can fit x2, but it cannot fit x1 and x2 at the same time. And I still want to compute softmax, right? Now, I want to compute softmax in such a way, though, that I don't have to have both parts in memory at the same time. Now, you could say, hey, why don't I compute softmax on the first half and then separately compute softmax on the second half? Why is that bad? Go for it.
Results.
Uh,
You get different results as you have different numbers.
Yes, yeah. I mean, the softmax involves a denominator. That's a summation of all the terms, not of half and half, right? So if I compute softmax separately on each component, well, that will be like computing softmax of 2 vectors, which is not the same thing. So I somehow need to integrate some global information into my tile calculation. Otherwise, I'll get the wrong answer. Everybody agree with that? So the game here is going to be, well, let's try to sort out how we can do this without, again, loading up the full vector into memory, which we can't do. There's too much memory. Okay, so let's try to kind of configure the calculation above in such a way that I never have to worry about either getting it wrong or using the full vector. Here's how it's going to work. The first thing basically is I'll compute the max as before over each component. So I have an m of x1, I have an m of x2, and then I'm going to compute these guys' max. And that's the overall max. Agree? The maximum of all the components in a vector is the maximum of the first and the maximum of the second components. That's a convenient fact about maxes. Okay, so for example, to compute this m of x, fortunately, I never need to look at the whole vector, even though max is a global operation over the whole thing. I can indeed do it in pieces and aggregate them by taking max again. Everybody agree with that? Cool. Okay, so I have my m of x, that's good. Now, I'm going to do the same calculation, my f of x, which was just going to be, hey, going ahead and multiplying by e to the minus m of x and exponentiating. I'm going to do the same thing, but again, I'll do it on the pieces so I can do it separately. Okay, so let's take a look over here. This is a more interesting expression. It's e times m of x1 minus m of x. Why is it like that? So normally, if we were just running the previous softmax procedure on each vector component x of 1 separately, what we would see here is e to the minus m of x1 times f of x1. Agree? I'm doing plug and chug on the expression above for f of x. And yet here something else appears, which is not e to the minus m of x1. It is e to the m of x1 minus m of x. Go for it.
Because you're multiplying because you're multiplying e to the m of x1 minus m of x, you're effectively like cross-canceling them out almost.
Yes, that is exactly what's happening, right? So the whole game here basically is really what I want to normalize by is the full m of x. But if I wanted to run the formula above, it would be m of x1, right? And that's exactly what this f of x1 is doing. It's saying, go ahead and subtract m of x1. So I have to correct for that, right? I have to add it back in and subtract m of x, which is the real thing. So everyone try this. Go ahead and plug in f of x1 with the formula up above and make sure that things cancel the correct way. All I'm doing is basically correcting so that I'm actually using the global maximum rather than the local maximum for each component vector. Okay, so I can do that, right? And how much extra information do I need for these things? Not too much, right? I need to store m1, m2, and the overall m. That's free numbers, so there's no big loss in doing this. Cool, so now I can compute this f of x in parts. I can do the first part, I can do the second part, and they are correct, right? And finally, I can do the same thing with my denominators, exactly the same calculation. And again, I can compute the first component's denominator and the second one separately. And then finally, I can go ahead and do my normalization. And by doing this, notice that I never had to load the full vector. Every single operation I'm doing is done on each separate vector with some extra pieces for adjusting the fact that we never saw the full thing. Yes?
I'm just trying to figure out, like, you will have to load the f of x1, or sorry, you'll have to load the tile to do f of x1, then load the tile to do f of x2, then load f of x1's tile again to do the transform on it as well, right? Or do you only need to load each tile once, essentially?
Once.
How do we not need to reload the f of x1 tile to do the transform on it after collecting the max and maxes?
Which ones are we talking about?
So for f of x, when we do the full calculation, we've collected max 1, the maximum max 1 and max 2.
Yeah.
So I'm wondering, how do we
Oh, yes,
renormalize
you
them?
have to. Yes, you do have to see them twice because
Okay.
you have to do a pass through. Yes, but you don't have to like keep it around, right? That's all I mean. Yes, I see your point. Cool. So all of this stuff was basically just saying, I don't need to materialize the full vector when I'm computing softmax. All I need to do is to operate on each component of that vector, and then I can adjust for the fact that really the component vector was a part of some greater whole. And what does it cost me in terms of extra stuff I had to keep around? Actually very little, right? All we had to do is to keep these m of x1 and m of x2 around, in addition to the global maximum m of x. Okay, now of course if we split these things into more than 2 tiles, sure, I'll have a few more of those objects, but they're all just numbers. They're not expensive to store. So this is pretty much the only trick. It just says things like be clever in the way you run these computations. Don't sort of blindly do them, because that gets expensive. You have to rely on going back and forth to the full memory. Just do it on each separate part. Cool. Okay, so this actually by itself is something really fast. The second thing is the trick that we talked about basically. We have this idea of, hey, let's make sure that rather than going ahead and keeping everything in memory for when we go do backprop, just go ahead and recompute things on the fly as if you were doing the forward pass. And by doing that, we can actually avoid this final cost, and I like this quote, repeatedly reading and writing of inputs and outputs from and to HBM. Cool. All right, now let's actually see what's going on. Here's the normal trade-off that I just talked about. We have this sort of intuitive idea that if I have to recompute stuff, that will cost me more time. If I recompute things 5 times, it's 5 times as slow as just doing it once. But if we avoid doing this stuff in a much more costly way, then even doing something 5 times is still much faster than doing it once in a much, much slower way. And let's go ahead and see the actual examples. Here's kind of what you get if you use flash attention instead of standard PyTorch-based attention. The amount of training that you end up getting is 3 to 3.5 times as fast for GPT-2 here, just because these experiments are academic budget experiments. But the same result that you get in general. And this is something that even the biggest labs training very large frontier models will end up doing. So that's the basic trick. It just says, hey, if you are more careful about how you use your GPU, you can be much faster. But notice that this doesn't require any real trade-offs or approximations. We didn't get rid of attention and replace it by some approximate attention that's faster. That's something else we could also do. We didn't have to say, hey, there's some special trick where we lose something and we gain something else. That entire trade-off was basically canceled just through a more clever use of where you store stuff. All right, so let me very briefly talk about another more general aspect. Flash attention was this plug-and-play technique that we could just go ahead and use. Here, we're going to have a lot more to look at when we start actually doing distributed training for large models. So the space of techniques here and the space of benefits that you get is way broader. We are going to spend all of 5 minutes on this instead of, a full semester to cover all the possible techniques. So, okay, let's suppose that I am training a model and I'm using my 1,000 GPUs. What would I do? What is the right way to take advantage of all of those devices simultaneously? And the normal story for when we go ahead and do distributed computing will look something like this. I have some central server that coordinates everybody. It has the full copy of the model, and that is sort of like the copy. And then what happens is it sends its copy to all of these nodes. Each of the nodes does a little bit of work on the model, and then once it's done, it sends its processed version back up to the top. And then the central server says, okay, let me aggregate all of these guys. That will be my sort of next iterate. And then I send all of this back to each of these computation nodes and tell them do a bit more work, and so forth. So this is what's called centralized distributed training. It's the easiest and simplest. Everything's always coordinated. Everything's easy to set up. But there's some downsides, and what are the downsides for us at least? Yeah? Yeah, so one thing that's going to be annoying for us is all this communication back and forth, right? So my computation node does some stuff. It has to send the full results of that to that central server. And then the central server has to send everybody back the final aggregate they got, and then keep doing this. So the communication costs here are very, very expensive. That's true. Another problem, of course, is for all of these nodes to each have their own copy of the model, that is also very difficult, right? If a node is a GPU, for example, well, there aren't any GPUs that are big enough for a 600 billion parameter model. We still have to break things up in some other way. So kind of our standard version of training here, where we just do synchronization, isn't really going to fly for large model training at least. So we'll have to do something different and more clever. And that means that we'll have to think of all the different ways that we do parallelization. So here's a few of them. Data is really the simplest. And in fact, even in standard distributed training, we will do this, right? Each of my nodes can look at some different slice of data and make an update based on its own slice of data. So splitting up the data among parts is a very standard thing in all cases. The second is, let's split up the weights. And again, this is the reason that this is motivated by the fact that we can never have the full model on a single GPU. And then finally, we may want to do things where we're more clever than just saying, okay, the first GPU gets the first layer's weights, the second GPU gets the second layer's weights, and so forth. If we do that, there are some downsides, which we'll see in just a second. Okay, so how many different techniques are there for different forms of parallelization for each of these? Thousands. And there's new ones proposed all the time. We're not really going to get into any of these, but I encourage everyone to read more about them. I do want to show this picture because I think this gives you a good sense of what's going on for parallelization. So here's one reason why you may not want to just say, hey, each of my GPUs gets a different layer, even though that's a very natural way of breaking things up. If you do that, let's suppose my device 0 there is my first GPU, and it gets F0, which is the function that computes the first layer of the network. Okay, then for me to have completed that first layer in the forward pass, I have to wait till device 0 is done. Only then does my next GPU, device 1, go ahead and get started with its own layer, F1. Everybody agree? And then similarly, I have to have my third device wait for the second to finish, and at this point there's only 4 layers in total, right? The forward pass is completed. For my third device, it starts the backward pass. All the other devices are not doing anything, they're hanging out waiting. Only when the backward pass is done for the third layer can I move on and do it for the second layer with the second device and so forth. So this is the process. Everybody has to be waiting on everybody else to conclude to do any work. And what that means basically is that most of the time, each device is doing nothing. Each GPU is, on average, just waiting. And in fact, the more layers there are, the worse your utilization. The more you're just doing nothing all the time. If I have 80 layers, then I'm only active 1/80th of the time, which is a really bad use of my GPUs. Go for it.
How significant, like in the bubble example you have below, how significant is the bottleneck at F33, P33?
Yeah, there's some overhead, right? And our job is to minimize that overhead versus the gains. But actually very insignificant as it turns out. Which is why we do this, right? Otherwise, it'd be pointless. Okay, so what is the solution to this problem of, well, I have to wait for each layer to complete before I do my job, which is to process the current layer, or to do backprop on their current layer? You can kind of guess it from this picture on the bottom. Any thoughts? Yeah.
Essentially, what you want to do is say, I'm going to hold 4 layers or 4 computations that we'll do, and then the next one will hold most of those computations as well, so that we can split the data up and start running it independently.
Yeah.
So like, device 0 will have 3
Yeah.
instances.
That's right, that's the game. Let's split up the computations at each layer in such a way that for each of those parts now, as soon as I'm done, I can send them upwards, and the next device can start working on those guys. In the meantime, I'm working on my next part. As soon as that's done, I send it upwards. Now the next device is ready for that one, and so forth. So that's what's happening over here. Notice how much overlap I can get between how much device 0 and device 1 is being used. There's only one small part where device 0 is in use, but device 1 is not. And vice versa, only one small part where device 0 is done, and device 1 is still operating. So this is our little pipelining trick here, also coming from very standard computer architecture ideas. You want to make sure everything gets split up in such a way that you don't have to wait for a conclusion before you start working on the next part. And what do we end up getting? Well, the kind of unused time, which is what you're seeing over here, is much, much, much smaller than what you're seeing on top. We get much higher utilization. And in fact, in all these cases, utilization is really what we're trying to capture. We want to get as close as possible to 100% use of our devices. Even though typically that's not possible because sometimes we do have to wait for something. Cool. Any short questions about this since we're about to run out of time?
But the weights will only get updated after one full backward proper, right?
Yeah, but I have to do a forward pass before I do anything else.
Yeah, for that we have done, but we can't optimize the middle one, like the weight till we get the latest updates to start with.
This is all just for computing a gradient, right? So this is just talking about computations that are necessary for a gradient, right? And this is one full gradient being computed right now. So we're not yet worried about moving on to the next gradient computation. We're just waiting to take this up. And notice, yeah, I see your point too. We're not showing any of the model itself here, right? This is just a breakup of computing the forward and backward passes into components. All right, we are out of time. Let me just start talking about the beginning of efficient inference. We'll conclude next time. This is almost the same story as training. And you might think, well, inference is cheaper and easier than training in some sense. Interestingly, that's not really true for really 2 or 3 different reasons. One reason is what I mentioned, which is that we do inference a lot more than we do training. Once I've completed training a model, I can use it a lot, right? I can run inference on it forever, more or less. The second thing is, if you kind of go back to our original Transformers story, we do have this interesting scenario where we can parallelize training, right? Because we have access to everything. All we have to do is go train. We can parallelize computing all of those attention layers. Unfortunately, we cannot do that for inference, right? We have to wait for each token to get generated before we create the next token. So this autoregressive non-parallelism is something painful at inference time that we don't have to deal with at training time. So therefore, for this reason, efficient inference is, if anything, more important than efficient training. And there's tons of different techniques that people have developed for it. I'm going to talk about a couple of them. One more thing that I think is interesting is in training, since you're running for a long time, I don't know, the differences are not quite as visible. At inference time, you're actually seeing the tokens get generated, right? So it's very painful to wait for them to get created very slowly. Okay, so we'll talk about 2 things, and today I'll spend a tiny bit of time discussing speculative decoding. We'll see some other techniques afterwards next time. For speculative decoding, it's a very clever idea that's not too different from what we've talked about, right? What is the slow part in our autoregressive generation? It's exactly what we said, right? We have to wait for this token to be created before we can get started with generating my next token. Everybody agree? So this is something that's annoying. Now, on the other hand, even at inference time, the time it takes to process stuff is pretty fast, right? So think of the prompt. I do have to run my entire prompt through the model at inference time before I can go and start generating the first token of the response. But running that prompt is fast, right? I can parallelize it. And I can do that because the prompt already exists. All the tokens have already been created. I do not have to wait for the 3rd token to get created before I start processing the 4th token. I can do all of these guys in parallel. Everybody agree? So filling in a prompt at inference time is fast because of parallelization, but actually generating tokens in my response is slow. I cannot parallelize that. Okay, we're going to try to take advantage of this idea. And the way that we can take advantage of this idea is something like this. Suppose that I don't have any way of generating tokens fast, but I do have a way of checking whether the tokens I've generated are reasonable. What is that way of checking? Well, again, basically all I have to do is to plug in the generated tokens that came from somewhere else and look at those probabilities and say, are they reasonable? Everybody agree? Filling stuff in that's already there is fast. And I can always check my probabilities and say, yeah, I think this is something that my model could have generated. Okay, so now what do I need? Well, I need someone else to give me those tokens, someone that's fast, and then I can approve of them or disapprove of them. That's going to be our basic idea. I'll just repeat it one more time. If there is some other person, model, thing that can generate tokens quickly, then my original language model can quickly check them by filling them in and seeing what those probabilities look like. And can do that in a parallel way. So it's fast. Everybody agree? So generating is slow, checking whether it's reasonable is fast. So let's try to do something where somebody else generates tokens for us, and then we'll check if they're good. Now, of course, it might turn out that we check and they're not good, and then we're not any faster. But if we ever see the case that indeed they're okay, then great, we saved a bunch of time. That is going to be the game that we try to play. All right, now where should these fast generated tokens come from? Who has a guess? Yeah.
Smaller L.
Yeah, exactly. I mean, this issue of how long it takes to generate things is a function of how big the model is. So let's just go ahead and use a smaller, what is a weaker language model. It's not useful all the time. We don't want to just rely on it. But it can give us some guesses, and then we'll check if they're good or bad. So this is going to be this idea of speculative decoding. It's going to say, hey, rather than me, as a big, slow language model, generating every token and waiting for the next one, I'll have a small, fast language model, make a bunch of guesses, and not just a few tokens, but maybe multiple copies of those few tokens. And then I'll go ahead and check those guys and see if any of them are okay. And if they're okay, I move forward. If they're not okay, then I'll say, okay, fine, I'm stuck generating my own token. And then we'll repeat this process in the hope that some of these guesses are happening to be okay all the time. And in fact, they are. And we can often speed things up by 2 times or more often. All right, we are way over time. Let's go ahead and keep going with this next week. Office hours this afternoon for anyone who has questions.